So here it is example 11. We have a piston cylinder device. It contains 50 liters of a liquid water at 40 degrees C and 200 kilopascal. Note that again we have a pair of pressure and a temperature. Okay, this one is the pressure, this one is the temperature. And heat is transferred to the water at a constant pressure case. Okay, here constant pressure is important because if we have constant pressure, then it reminds us to find out what is that if the liquid goes from saturated liquid to saturated vapor, then the energy input should be equal to the enthalpy instead of the internal energy. Okay, I will explain more in the next chapter. Okay, until the entire liquid is vaporized. Okay, and we need to find out the mass, the final temperature, the total enthalpy change, and show the process on a TeV diagram with respect to the saturation lines. Saturation lines just means the saturation dome I have set before. Okay, but before you really start this problem, I advise you to first start on this part first. Okay, without this part, you cannot get what's really happening. Okay, so better start on part D first, and then so pause this video now. Okay, let's see the solution. Okay, let's do part D first, as I've said. First, let us have a rough sketch on the process on a TeV diagram. Okay, let's draw the TeV axis here. So we have T and V. And after that, let's draw the saturation dome. Okay, rough sketch is okay. And here note that this liquid water, because we have this pair of pressure and temperature, okay, our usual procedure is that in order to find out whether it's compressed or superheated, we will first go to the saturation table first. For example, in this time, I go to table A4. We go to 40 degrees C, and you can find that the pressure is this one, 7.3851, which is smaller than the given pressure, that is 200 kilopascal. Okay, in this case, because the given pressure is much greater than this, so it should be in a compressed liquid state. As a result, the state 1 should be somewhere here. But what is stage 2? Well, the final state is that the entire liquid is vaporized, so it would follow this heating curve. Because it's a constant pressure, so it just follow our usual heating curve. So we will go to stage 2. And usually, in order to show the direction, we would add arrows to it. So it goes from stage 1 to stage 2. This is part D. Okay. So from this schematic, we know several things. First one, compressed liquid, and then it will go to saturated liquid at a constant pressure, and then it just go horizontally. So this example actually gives you a chance on constructing a TeV diagram, and it is important, okay, especially in later chapters. We need to rely on the schematic to solve the problems. Otherwise, you would not know what's going on. So let's go back to part A. We need to find out the mass of water. But how can we find out that? Okay, as I've said that, if you go to table A4, then you will see that 40 degrees C would correspond to the saturation pressure of 7.3851 kilopascal, which is smaller than 200 kilopascal. As a result, we say that in this case it is a compressed liquid. So we will either go to the compressed liquid table or we just using the approximation. But most likely, we would need to use the approximation, because if you really go to table A7, then you will see that we just have a very narrow range of data. This is a compressed liquid water table. The smallest pressure available is 5 megapascal. But in this case, we just have 200 kilopascal. So we do not have a sufficient data. As a result, we need to go back and use our approximation. Okay. So in order to find out the mass, because we have this total volume of this container, so after we find out the specific volume, we just divide the volume by the specific volume to find out the mass. Okay. So we will have part A. The specific volume will be approximately equal to the specific volume at a saturated liquid state at that temperature, 40 degrees C. Just check the temperature table. You will find that equal to 0.001008 meter cube per kg. And this is from table A4. After that, we find out the mass. The mass is equal to big V divided by small v. The big V is 50 liter. If you change to meter cube, it will be 0.050 divided by 0.001008. That's the specific volume. Finally, you will find it equal to 49.60 kg or 49.6. So this is our part A. Part B, we need to find out the final temperature. What's the final temperature? Okay, this F is not talking about saturated liquid state. It's just equal to final. The final temperature is the saturation temperature at 200 kilopascal because it's a constant pressure process. Okay, so you just go to table A5, 200 kilopascal. So here, so we get 120.21 degrees C. Okay, part B is done. So how about task C? We need to determine the total enthalpy change. Total enthalpy change. Total means that we need to multiply the specific enthalpy by the mass to get the total enthalpy change. However, first of all, we need to find out delta H. Okay, the delta H should be equal to the mass multiplied by H2 minus H1. Okay, final enthalpy minus the initial enthalpy. But what is H2? What is H1? We need to find out that. For H1, we will use our approximation given in the table. H approximate equal to HF at the temperature. We have given the temperature to be 40 degrees C. So HF at 40 degrees C. Okay. And here you just go to table A4. You will find that this is equal to 167.53 kilojoule per kg. How about H2? H2, if you see in this diagram, it lies on the saturated vapor line, and here it should be the enthalpy at the saturated vapor state at 200 kilopascal because it's a constant pressure process. So Hg at 200 kilopascal is 2706.3 kilojoule per kg. Okay, you can find these two values directly. This is from table A4, while this one is from table A5. And what you need to do is to plug in those values. So delta H equal to the mass. We have found out the mass already. And enthalpy change. So 2706.3 minus 167.53. And finally, you get the answer, 126,000 kilojoule. Okay, great value indeed. But for the delta H, because of the great mass, you should get this kind of magnitude of the delta H. Okay, so trust yourself. If you see this kind of magnitude of thing, don't be afraid. Okay, because usually delta H is quite big. Okay, so we have done this example.